to my next case. My next case, that is the case third. So, my next case is the case where f is completely a function of explicitly a function of x and y prime. So, there is no explicit dependence of y on the integrand f. So, in this case my functional will have the following form: j of y is integral from y0 to y1 f of x comma y prime dx. Okay. And then if we recall, my Euler-Lagrange equation involved partial derivatives with respect to y and partial derivatives with respect to y prime. So, the partial derivatives with respect to y is going to vanish because there is no explicit dependence on y in this integrand. So, in that case, so in this case my Euler-Lagrange equation reduces to the following simple form: partial f partial y prime is equal to a constant C1, right. So, that can be very quickly derived from the Euler-Lagrange equation. Now, one example that comes right away is the example of geodesics on the surface of a sphere. Well, the geodesics on the plane is nothing but straight line, and that falls in the case 1 discussion. In case 3 discussion is the geodesics on a sphere. This is one very nice example. Okay. So, let me just recall, in our first lecture I had introduced the functional for the geodesics on a sphere. So, let us recall from our first lecture that my geodesic or my path functional, we are trying to minimize the path of a curve lying on the surface of a sphere, right. So, my path function L of u comma v, now we have two parameters involved, is an integral from t0 to t1 of the square root of u prime square plus v prime square sine square u dt, where these derivatives u prime and v prime, these are the derivatives taken with respect to the parameter t. So, then this integrand, we reduce this integrand to a slightly more convenient form by taking another set of variables. Let us say that my variables u is substituted with theta. So, instead of u I am going to use the variable theta. These are all dummy variables, right, and instead of v I am using the variable phi, right. So, in that case my integral becomes j phi is integral from theta 0 to theta 1 square root of 1 plus phi prime square sine square theta and d phi d theta, where this phi prime is nothing but d phi d theta. So, what we have assumed is theta is our independent variable and phi depends on theta, right. So, we have completely removed the parameter t. So, instead of working in the parametric form, we are now directly working in the form of the two variables theta and phi, right. So, let me call this boxed expression as 3, and let me now. So, again notice that in this particular integrand we only have a function of theta which serves as x. So, theta is my x and phi prime is my y prime. So, this particular integrand is only a function of x and y, right. So, which means that I can directly use this boxed form of Euler-Lagrange. So, using this boxed form, using 3, I see that my extremal is going to satisfy. So, I am going to directly plug my small f. So, this is my small f. In 3, I see that the expression reduces to phi prime sine square theta divided by 1 plus phi prime square sin square theta, right, and this is also equal to C1, which is the constant. So, the next set of steps will involve solving this boxed, let me call this another expression. Let me say that this equation is 1. So, the next set of steps will involve solving this equation 1. So, before we do that, notice that the quantity in the denominator is certainly bigger than the quantity in the numerator, right. So, it cannot, so the quantity in the numerator cannot exceed the quantity in the denominator, because the sign is not sign function is bounded above by 1. So, we are guaranteed that the quantity in the denominator is bigger. So, what this says implicitly is the following. It says that my constant on the right hand side, notice that the constant, if this particular quantity is less than 1, right, which means that the absolute value of the quantity on the right hand side is also less than 1. So, I have that C1 is less than 1, right. So, which means I can replace C1 by let us say a quantity which is bounded above by 1, replace C1 by sin alpha. We will soon see why we are doing that, and from here we let me rewrite my equation for the extremal. We see that sin phi, so phi prime sin square theta divided by whatever was written in the denominator, that is equal to C1. So, I am just recalling here. So, this is now, instead of using C1, we have now replaced with another constant, and let us separate out phi prime completely from this expression. We get that phi prime is sin alpha divided by sin theta times square root of sin square theta minus sin square alpha. Okay. So, then the next step will involve integrating phi with respect to theta, right. So, let me just write that step. So, phi is integral from theta 0 to theta 1. So, notice that since we are using the limits theta 0 and theta 1. So, let me just change the variable theta with another dummy variable zeta, right. So, my integration will involve integrating this particular quantity sin alpha d zeta divided by sin zeta times sin square zeta minus sin square alpha plus a constant of integration, let me call this as beta. So, beta, where beta is nothing but phi at the original point, the starting point theta 0, right. So, that is my constant. So, then once we integrate, well, I am not going to go through all the steps of the integration, because that is part of the students who have done multivariate calculus, but let me write down the final answer after integrating. We see that after integrating my phi plus beta, I have now taken beta on the other side, right. Phi plus beta of cos of this angle is equal to tan alpha divided by tan theta. So, after integration we get the final answer, which looks as the following, and then we can further simplify by opening up this cos a plus b using the cos a plus b formula. We see that this is equal to cos beta, cos phi cos beta minus sin phi sin beta is equal to tan alpha divided by tan theta, which is sin theta times cos theta, right. So, if we now transfer this on the left hand side, we see now, notice what is the new expression now. So, I am going to very carefully write the left hand side. This is sin theta times cos phi times cos beta. Let me just club these first two terms, minus sin theta times sin phi times sin beta. So, let me just club the second of the first two terms of the second expression. So, this is also equal to tan alpha cos theta. Notice that recall the parametric form, of points on sphere. So, students should recall the parametric form of the points on sphere whose x component is nothing but r sin theta cos phi, r sin theta sin phi and r cos theta. So, x is r times this, y is r times this and z is r times this. So, which means that if we multiply throughout by r, where r is the radius of the sphere we are talking about, we can rewrite, let me call this new expression by 1 prime. So, we can now rewrite 1 prime as follows. We can rewrite in Cartesian coordinates that my equation has boiled down to the following expression: x cos beta minus y sin beta is equal to z tan alpha, right. So, we see that where x, y and z, they are on the sphere, they are on the surface of the sphere surface, right. And further x, y, z, they satisfy this equation of a plane which passes through the origin, because x equal to 0, y equal to 0 and z equal to 0 certainly satisfies this equation. So, my extremal, so the moral of the story is that the geodesic or the extremal solution lies at the intersection of the sphere and the plane which passes through the origin, right. So, geodesic lies on the intersection of the sphere and the plane passing through the origin, right. It lies on the intersection of the sphere and the plane passing through the origin, and that can only be, if I were to draw a sphere, let me just show the diagram quickly. So, here we have a sphere and here we have a plane, which cuts the sphere and it passes through the origin, and then the intersection of this plane and the sphere can only be an arc which is the equator of the sphere, which is the great circle, right. So, that is the great circle, right. So, the great circle is one of the equator circle with the largest diameter, right. So, that is the geodesic on the sphere. Okay, so then let us look at another example which falls under this case. Very interesting example, that is how light travels through different medium. So students who have done science in class 12th, they must have recalled the Snell's law and the Fermat's principle of geometric optics. Namely, if we have different media, we have that the light follows a path such that certain relation is satisfied. So, students in class 12th are taught certain relations on how the light travels through different medium. In today's lecture, I am going to show it using calculus of variations as to how to get that result. Okay, so the result is as follows. So, the Fermat principle says that light travels along a path. See, nature always follows a principle such that it obeys the minimum energy, minimum time, minimum path and so on, right. So, in this case, the light is going to travel along a path between 2 points such that the time between the travel of these 2 points is minimized, such that the time taken is minimized. Okay. So, to set up this problem, let us say that the speed of light, in general, the speed of light depends on the medium in which it travels. So, it depends on the media. Let me denote the speed of light by c of x comma y. So, it depends on, so I am doing a problem in 2 dimensions in Cartesian coordinate x and y. So, let me say that in general the speed of light depends on both the coordinates x and y. So, the Fermat's principle says the following. The Fermat's principle is nothing but the statement that I have just written. It says that light, the light path, the path of the light will be a minima of the following functional, right. So, the functional that we have is the time functional. So, the time functional is the integral of the arc length or the length of the path travelled by the light divided by the speed of the light, which is the time. So, the integrand of this integral is nothing but the total time taken by the light to travel from point x0 to x1. So, rewriting this arc length in the form of the xy Cartesian coordinates, you see that this is also equal to 1 plus y prime square divided by c of x comma y dx. Okay. So, then in order to further solve this problem, let us use a simplifying assumption, right. So, I want to show the solution to this problem. So, let us look at a simplified scenario. So, let me call this as a special case. So, the special case is we have c of x comma y is given by, let us say, 1 by g of x, right. So, I have used a simplifying assumption that the speed of light purely depends on the x coordinate of x component of the coordinate system. So, in this case my time functional becomes integral from x0 to x1 g of x times square root 1 plus y prime square dx, right. So, what we have is, let me call some of, so I have to rename some of this expression, otherwise we are going to lose track of these expressions. So, let me notice that now this assumption has completely made this functional as in such a way, defined this functional in such a way that the integrand is purely a function of x and y prime. So, this is falling under the category of case 3. So, we see that let us go back few slides. I am going to use the result which is this boxed result. We are in the case 3. So, my Euler Lagrange is going to satisfy this boxed result given by 3. Okay. So, let me use the boxed result 3 to see that my extremal is going to satisfy the following expression g of x times y prime divided by 1 plus y prime square root, which is also equal to constant which is equal to C1, right. Okay. So, then let me just rewrite this expression. We see that this is y prime divided by 1 plus y prime square, which is C1 divided by gx. Now, notice that the quantity on the left hand side will most necessarily less than equal to 1, right, and so which means that, well, let me just take the square, and it's better, it's clearer that way. So, taking the square, we see that y prime square divided by 1 plus y prime square is equal to C1 by g of x whole square. Notice now that the quantity on the left hand side is less than or equal to 1, right. So, which means that the quantity on the right hand side will this is not less than equal to, but strictly less than 1. So, which means that the quantity on the right hand side is also strictly less than 1, and this helps when we write y prime purely as a function of x. We see that y prime of x is equal to 1 by square root g of x divided by c1 square minus 1, right, or we see that y of x is equal to integral. We integrate this expression. Notice that this quantity is greater than 1 because the quantity here is less than 1, right. So, the square root is well defined. So, integrating this expression, I see that this is what we are going to get. So, g square by c1 square minus 1 plus another constant of integration, which is I define as c2. Okay. So, then the further integration of this expression is not possible unless and until we know the exact form of this function g, but we can go ahead and see some intuitive results. We can still extract the physics out of this problem. Before we do that, we must mention the following. Well, y is the extremal, so we must have that. First, y has at least two continuous partial derivatives, that is the underlying assumption of the Euler-Lagrange equation, and that is fine as long as the velocity here defined by this function g is continuous, right. The moment we have discontinuities, we have some problems, right. So, let me look at the case. So, what I have just described is as follows. So, consider the fact, suppose let me draw the figure. So, suppose we have two media, let us say we have air and we have water. So, just an example here, right. So, we have two media and we have light which passes through the first media and the light which passes through the second media, and of course, the speed of light in the first media will be very different from the speed of light from the second media, which means that in this case c of x comma y will have discontinuities, right, either discontinuity of first order or second order and so on, right. So, the speed of light is different from in air than in water, and we will see that light travels very differently in the different media, right. So, in this case now I cannot use my Euler-Lagrange equation to solve the problem, because the moment the velocity has discontinuities, the speed has discontinuity, we cannot use our underlying assumption of having two continuous derivatives of the integral will fail, right. So, then we can still move ahead. So, let me just draw this problem a little bit more carefully. So, this is my horizontal. Let me say that the speed of light, this path taken by the light makes an angle phi naught, right. It makes an angle phi naught, and the path taken by the light in water in the second medium makes an angle phi 1, right, with the horizontal, right. So, in this case what we are going to do is, well, of course, there are discontinuities when we consider the problem with two media, but in each of the single medium problems the path taken by the light has continuous solution. So, we can definitely apply our Euler-Lagrange equation in each of the media and try to combine the solution somehow, right. So, the idea is as follows. What we do is we break the problem into two problems, break into two problems, we break into two problems with boundary points with boundary points x star comma y star, right. So let me call this boundary point as x star comma y star, such that we do a little bit more simplification, such that my x star, the x component of the point or the location, the x component of the boundary point is fixed, and I have movable y star, right. So this point, so moving the y star is going to change my angles phi naught and phi 1, but my x star, my x component of the location of the boundary is completely fixed, right. So in that case my integral j of y, which was my time integral, can now be broken down into two integrals, one integral from x0 to x star, right, and the other integral from x star to x1, right, and in each of these integral the path of the light is a continuous function. So we see that the path is 1 plus y prime square dx divided by the speed of light. Let us say the speed here is c0 and the speed here is c1. Since within a single medium the speed of light is assumed to be fixed and constant, it is only with different mediums the speed changes, right. So which means that in the first medium, let me call this speed of light is c0, and the second medium the speed of light will be c1, right. So now we see that each of these integrals, in the integrand of each of these integrals are purely a function of y prime. So this each of these functionals, individual functionals, they fall under case 1, or the solution to, or the extremal solution to these functionals are nothing but straight lines, right. So this is all geodesic on a plane. So this is the solution, the extremal solution will be all geodesic on plane which are straight lines, right. So let me right away write the solution. The solution y of x will be straight lines, such that the first straight line passes through x naught y naught comma x star y star. So let me write the equation of the straight line. So x is less than equal to x star and x minus x star y minus y naught minus y1 minus y naught divided by x1 minus x naught plus y star x greater than equal to x star, and let me call this solution by an expression A, by the quantity A. So notice now we have completely, so x naught, y naught, x1, y1, x star, these are all fixed quantities, except now we have just one variable y star, which is the variable of the problem to begin with, and now the solution to this combined problem will involve minimization of this function with respect to this variable y star. So which means my final solution, to get my final solution, we have to do as ordinary minimization or the multivariate minimization with respect to the parameter y star. So explicitly compute well, we explicitly compute j of y and minimize with respect to the variable y star. Notice now we are not doing a functional optimization, but we are doing an ordinary function optimization. So we use the standard first derivative, second derivative tests to find the quantity y star which minimizes our function y.